Good evening, sir. You can start now, sir.
Okay, ma'am. Thank you so much. Good evening, students. Yes, today we are going to continue our discussion on electromagnetic induction. So the first concept which I am going to discuss today is induced electric field. After that, we will be discussing eddy currents, AC generator and all. Okay. So now I will be discussing the concept of induced electric field. So what is meant by this induced electric field? So for that we need to consider a diagram here. So you should consider that this is a circular conducting loop. Okay. So this conducting loop is placed perpendicular. It is placed perpendicular to a uniform magnetic field B. Okay. So here you have the uniform magnetic field represented by these dots. So the dots represent the uniform magnetic field. Okay. So this conducting loop, so this magnetic field is represented by B of T. That is, the magnetic field B is changing with time. So that's why it is a function of time T. And this circular conducting loop is placed perpendicular to this uniform magnetic field varying with time. So due to the time varying magnetic field, what happens is a current is induced in the conducting loop. Okay. So here you can see the current is induced in the conducting loop like this. So originally the charges in the conducting loop are actually stationary. So how do we get induced current here? Okay. How do we get the induced current here? Because here you will be getting some electric force, okay, induced electric force and also induced electric field, okay. So what is our conclusion is that when a conducting loop like this is placed in a time varying magnetic field, the changing magnetic field actually causes an electric field or it induces an electric field in this loop. So this induced electric field causes a potential difference within this conductor, okay, this circular conductor, and this manifests as the induced EMF in the loop. Okay. So due to the induced EMF and induced electric field, you will be getting induced current. So the time dependent magnetic field causes the induced electric field in a conductor. This is the concept. And now we will be discussing the induced electric field due to a time varying uniform cylindrical magnetic field. Okay. So now we are going to discuss induced electric field due to a time varying, okay, due to a time varying cylindrical magnetic field. So you should consider that the magnetic field is in cylindrical shape. So cylindrical magnetic field. So this is the concept. So for that we need to once again consider a diagram. So let me draw that diagram now. Here I am showing you the cross section of the cylindrical magnetic field. So inside this circle, I am considering one more circle. Okay. So this figure actually shows you the cross section of the cylindrical magnetic field with capital R as the radius of cross section. So of course here you see from here to here the radius is given by capital R. Capital R as the radius of cross section, and the magnetic field can be shown like this. Okay, this into mark or cross mark, whatever you call that. This is the magnetic field. So let us consider a point P, okay, at a distance small r. So I will be considering a point P at a distance small r. So the point P is lying somewhere here. Here. The point P at a distance small r from the center. Okay, this is the cross section of a cylindrical magnetic field. So here the magnetic field B, which I have shown by these black color cross marks. So this magnetic field is actually uniform, but it is a time varying magnetic field. So the magnetic field is actually given by dB by dt. It is varying with respect to time. Now at this point P, we are going to calculate the induced electric field. Okay, induced electric field due to the time dependent and varying magnetic field. At the point P, what is the electric field that we are going to calculate? So when we calculate this, we will be getting this actually induced electric field is given by this formula. E induced equal to minus A divided by 2 pi R into dB by dt. Okay. So this is the formula. So this is our formula. A is the area of cross section. For this concept, we will be having some cases. The first case is small r is very much lesser than capital R. That is shown in the diagram itself. The small r, as you can see, the small r is very much lesser than the capital R. So the first case I will be writing here, small r lesser than capital R. In this case, what is your induced electric field? So that is E induced equal to minus pi r square divided by 2 pi r into dB by dt. So when you simplify this, you will be getting minus r by 2 into dB by dt. This is your expression for the induced electric field due to the cylindrical magnetic field. Okay. And the second case we will be discussing here is small r greater than capital R. So here the induced electric field is given by E induced is equal to minus pi r square divided by 2 pi into small r into dB by dt. So this is the induced electric field in this case, and when you simplify this further, you will be getting minus r squared by 2r into dB by dt. So here small r greater than capital R means this point P lies somewhere outside this red color circle, okay, this outer circle. So in that case, you will be getting the induced electric field by this formula. And the third case we will be discussing is small r equal to capital R. Okay, so small r equal to capital R. In this case, your induced electric field is actually maximum. So that is R by 2 dB by dt. Okay, and based on all these equations, we can show the variation of this induced electric field with the help of a graph. We can show the variation of the induced electric field with the distance small r, and how we can show this variation. We can use a graph to show that. So here you see, this is the graph. So your induced electric field is along the y-axis, and your distance is along the x-axis. Okay. So here the variation can be shown like this. The induced electric field rises sharply, okay, and after that it falls like this. Okay, so here you see it reaches the peak at small r equal to capital R. Okay, small r equal to capital R, the induced electric field reaches a maximum. So here you see it is E max. Okay, it is E max. So this is the concept of induced electric field due to a time varying cylindrical magnetic field. Okay. Now we will be discussing the concept of eddy currents. So does anyone have any idea about this eddy currents? Do you know anything about this, students? Whatever you know about the eddy currents, you can tell me. Yes? The concept of eddy currents, do you know anything about this? Students, does anyone know anything about this? You can tell me. So eddy current means when a changing magnetic field, okay, is linked to a metallic conductor or a bulk piece of conducting material. Okay, so when a changing magnetic field is applied to metallic conductors. Okay, when it is applied to metallic conductors, you can see the formation of eddy currents inside the conductor. Circulating currents, they are actually, so that's why they are called eddy currents. Okay, so circulating currents called eddy currents are developed inside the materials. Okay, so these eddy currents lead to production of heat inside the conductor, and they are otherwise called as Foucault currents as well. Okay, Foucault currents as well. So these eddy currents have advantages as well as disadvantages. So advantages, it can be used in a deadbeat galvanometer. Okay, this concept can be used in deadbeat galvanometer. So in a deadbeat galvanometer, the pointer actually comes to rest immediately due to the presence of eddy currents. Okay. Otherwise, the pointer may be fluctuating here and there when current is flown through the deadbeat galvanometer. But the pointer actually, after coming to the specific set of readings in the deadbeat galvanometer, it comes to the equilibrium position immediately because the eddy currents actually opposes the motion of that pointer. Okay, because you know very well about the Lenz's law. Actually, the induced current flows in a direction to oppose. Okay, the change causes it. So due to that concept, the pointer, whenever it is moving, eddy currents start developing inside the pointer, and that eddy currents actually oppose the movement of the pointer. So whenever the pointer comes to the equilibrium position, it opposes the further motion of the pointer. The eddy currents opposes the further motion of the pointer. So this is the advantage of eddy current, and of course, electric brakes are also application of these eddy currents. You can find many number of applications of these eddy currents actually, and in a speedometer also you can see the needle or that pointer. Okay, that comes to rest immediately due to the presence of eddy current. Okay, so there are many ways to reduce the eddy current, actually eddy current loss actually, because eddy currents lead to unwanted generation of heat. So there are many ways to stop the eddy currents or to reduce the effect of eddy currents. One of them is to laminate the conductor. Okay, so when you laminate the conductor, you can reduce the eddy current loss. Okay, right. So with this small information about the eddy currents, now we are moving to LR circuits. Okay, now we are moving to LR circuits. LR circuits. LR circuit means L means inductor coil, okay, and R means resistance, okay. So L means inductor coil, R means resistance. So now let me show you the circuit here. Circuit actually looks like this. So here you may be having the resistor and inductor coil. Okay. So here the resistance is there, shown by capital letter R, and the inductor coil, it is shown like this. Okay. So here you are having the inductor coil. Here actually there is a key. Okay, there is a key here. Here there is a key. So this is the position initially. And here you will be having a cell to supply the EMF. This is the positive terminal. This is the negative terminal. Okay, this is the positive terminal. This is the negative terminal. The current flows in this direction. The current flow is in this direction, represented by I. So here you have the position B. Here you have the position A. Okay. So when this switch is moved to the position A, okay, what happens? The cell is connected to inductor and the resistance. Okay. So now we are going to discuss the growth of current in this LR circuit. Growth of current in this LR circuit means when the switch is connected to the position A. Okay, when the switch is connected to the position A, what happens? The resistor and inductors are connected with the cell of EMF E. So what happens is the current starts flowing through the resistor and inductor, and the current actually grows from 0 to the maximum value or any desired value, but the current actually starts growing from the 0 value. So when current flows through the resistor and inductor, the inductor actually opposes the growth of current due to the back EMF. Okay, so due to the presence of this inductor, a back EMF is generated which opposes the growth of current in the circuit. Okay, due to that, what happens is the rate of growth of current in the circuit is actually reduced. Okay, so now we will be discussing the concepts of growth of current here. Growth of current in LR circuit. Growth of current in LR circuit. Growth of current simply it is due to the introduction of the cell of EMF E here. So here when you bring the switch position to the point A, current starts flowing through the circuit and current grows from 0 to the desired value. And what is the final expression for the current? That is small I equal to, okay, E by R within the bracket 1 minus exponential minus R by L into T. Okay. So this is the expression for the current flowing through the circuit, and the maximum current. Maximum current is represented by I naught, and I naught equal to E by R. Okay, E by R. So this expression can be modified like this: I equal to I naught within the bracket 1 minus exponential minus R by L into T. Okay. So this is the expression for the current. This is the expression for the current flowing through the circuit. And of course, you can also simplify this equation or write this equation in another form. So what is that form? That will be I equal to I naught within the bracket 1 minus exponential minus T by tau. Okay, minus T by tau. Here, what is tau? Tau is nothing but it is L by R. Tau is L by R and it is called the time constant. Okay, it is called time constant. So I equal to I naught. So let me write that here. I equal to I naught within the bracket 1 minus exponential minus T by tau. Okay. Here tau equal to L by R, that is called the time constant. Okay. So here, when your time, small letter t, okay, when your time t is equal to, when the time t is equal to tau equal to L by R, what happens to the current? I equal to I0 1 minus exponential minus 1. Okay, according to this equation, instead of t, you need to substitute tau. So tau by tau, it is 1. You are having negative sign here, that is exponential minus 1. So that means I equal to I0 into 1 minus exponential minus e means 1 by e. Okay, and that will give you 0.63 I naught. So what is the meaning of this? After the time interval of tau, okay, after the time interval of tau, the current reaches the value of 63% of the maximum current. Okay, so how will you define the time constant? Time constant is nothing but the time in which the current rises from 0 to 63% of its final value. Okay, so this is called time constant here. Okay, so one more thing which I want to tell you is that, as I have mentioned you already, when the cell of EMF E is connected in the circuit, current starts flowing through this. Initially, the growth of current, the rate of growth of current is increasing, but after a few seconds, due to the presence of this inductor coil, the growth of current is arrested and there will be decrease in the growth of current, rate of growth of current. Okay, so as your I tends to I naught, as your current tends to the maximum current, what happens is it will be reaching 63% of the maximum value. Actually, not 63%. Actually, when the current becomes I naught, I becomes I naught, or when it tends to become I naught, what happens is the rate of growth of the current is actually decreasing due to the presence of this inductor coil. Okay. So this is what the growth of current in LR circuit is all about. And now we will be discussing the decay of current in LR circuit. Okay. So here now we will be discussing the concept of decay of current in LR circuit based on the same circuit. So this circuit you should keep it in mind, and let us discuss decay of current in LR circuit. So decay of current in LR circuit means, as you see from this circuit, you should consider that initially the switch S is connected to the point A, okay, for a long time, and due to that the current in the circuit tends to reach the maximum value I naught. Okay, for a long period of time the switch S is initially connected to the point A, and due to that the current tends to reach the maximum value I naught. Now what happens is, suddenly you disconnect the point A and the switch is moved to the position B. Okay, switch is moved to the position B. Now what happens? The circuit is now disconnected from the battery. Okay, circuit is now disconnected from the battery, and what happens is the current in the circuit begins to fall. Okay, so if there is no inductor coil here, the current in the circuit immediately falls to 0. If there is no inductor coil in the circuit, if you change the switch position to the point B, the current in the circuit would have fallen immediately to 0 if there is no inductor coil. But here you have the inductor coil. The concept of inductor coil is that here the back EMF is generated in such a way that it opposes the change that causes it. Here what is the change? The current through the circuit is decreasing, and due to that EMF is generated in the inductor such that it opposes the fall of current. Okay, it opposes the decay of current. Due to that, what happens is the rate of decay of current is actually reduced here. Okay, exactly the opposite effect. Here, the rate of growth of current in the LR circuit is slowed down due to inductor coil. In this scenario, that is the decay of current in LR circuit, the rate of decay of the LR circuit is reduced due to the presence of the inductor coil. So here, what is the expression for the current? Okay, that is I equal to I naught exponential. Here there is a little bit change in the equation. Here, how will you write the expression for current? I equal to I naught into exponential minus R by L into T. Okay. Actually, the time should be inside the exponential. Okay. That's the correct way to express. So I equal to I naught exponential minus R by L into T. So this can be simplified to minus T by tau. As you know very well, tau equal to L by R. Okay. Tau equal to L by R. That is the inductive time constant of the circuit. So the current here decays exponentially. From this equation, you can understand that very well. I equal to I naught exponential minus T by tau. That is exponential decay of current. So now we should consider the case when your T is equal to tau, okay, or L by R. When your T is equal to L by R, what happens? That is the case. So when T equal to L by R, what happens to the current? I equal to I naught exponential minus L by R divided by tau is also L by R. So that will be I naught exponential minus 1. Okay, I naught exponential minus 1. That means I naught by E. Okay, I naught by E. So I equal to I naught by E. When you substitute the values, what you are getting is I equal to 0.37 into I naught. That means at T equal to L by R or tau, the current reaches 37% of the maximum value, or the current falls to 37% of the maximum value. Okay. So this is the thing which you need to keep in mind. The current, when it reaches or when it falls down to 37% of the maximum value. So that is actually the time constant. Okay, when the time is equal to the time constant or the inductive time constant. Okay, I equal to 37% of I naught. 37% of I. Now the rate of decay of current here. Okay, the rate of decay of current we need to express here. The rate of decay of current is represented by this equation, that is minus di by dt is equal to R by L into I. Okay, this is the expression for the rate of decay of current in the LR circuit. So you may be getting numerical problems based on this. So you should remember the formula and everything. Okay. And now we are going to discuss the concept of transformers. So a transformer is the device which works on the principle of mutual induction. So here you are having a primary coil. Okay. And here you are having some core. And you will be having a secondary coil here. Due to the flow of current in the primary coil, EMF is induced in the secondary coil, and this is called mutual induction. And this mutual induction is the concept used in transformers. Okay. So we have certain equations for this transformer. So let us discuss those equations. ES divided by EP. ES divided by EP equal to NS divided by NP. So here what is meant by ES? EMF induced in secondary coil. So ES is EMF induced in secondary coil, or you can simply say secondary, and EP is the EMF or the back EMF in primary. Okay, primary. And what is NS? NS is number of turns in secondary. NP is the number of turns in primary. Okay, number of turns in primary. So this is one equation. Here NS by NP is otherwise called the transformer ratio, represented as K, turn ratio or transformer ratio. So this is called turn ratio or transformer ratio. And for an ideal transformer, you will be having this equation as well. For ideal transformer, your input power will be equal to output power. Okay. So for ideal transformer, input power means EP into IP. That is voltage across the EMF across the primary into current across the primary. So EP IP is equal to ES IS. This is the expression for ideal transformer. So ES by EP, from this ES by EP equal to IP by IS. This is equal to NS by NP. So these are the important equations. You should solve the numerical problems based on these equations. Okay. And in a transformer, you have two types, that is step up transformer and step down transformer. So step up means whatever EMF you are supplying to the primary, the EMF is actually increased as the output. Okay, step up. Step up means the voltage supplied to the primary is actually increased. Okay, by changing the turn ratio, you are actually increasing the voltage. Okay, so that is called step up transformer. The low voltage is converted into high voltage at low current. So here the number of turns in the secondary coil is greater than the number of turns in the primary coil. So N S is greater than N P. So due to that, EMF is in secondary is greater than EMF in primary. But as far as current is concerned, IS is lesser than IP. Okay. So these are the equations for, and of course we have a step down transformer as well. So step down transformer. So for a step down transformer, all the equations are reversed. Okay. Here the number of turns in primary coil is greater. That means Ns lesser than Np. So due to that, what happens? Es lesser than Ep. Is is greater than Ip. Okay. So these are the equations for primary and secondary transformers. So there are of course many losses in the transformer as well. Okay, eddy current loss, hysteresis loss, like that. And we are not going to discuss all those things in detail. Okay, so those are just uh, theory side. Okay, so we don't have to discuss that in detail. So these are the things which you should keep in mind as far as transformer is concerned. So now we will be discussing the concept of AC generator. Okay, AC generator. Can anyone tell me what is the meaning of this AC generator? Yes, students, can anyone tell me what is the meaning of this AC generator?
Sir,
Yes, please.
so the device used to convert mechanical energy into electrical energies.
Yeah, absolutely right. So whatever generator which you use in your home or cinema theaters or big shopping malls, okay. So in all those places we need alternating current, right? Because in our home, whatever current we receive, okay, in all the plug points in our home, so all these currents are actually alternating currents. Okay, alternating currents. So that alternating current is required for us in case if there is any power shutdown from the electricity department. So in those situations, we use the AC generator. Okay, we use the AC generator. So that is nothing but an electrical machine which converts the mechanical energy into electrical energy. So how does it work? Okay, so let me quickly draw that diagram so that you can understand it better. So here you see you have a coil, rectangular coil like this. And the position of various points can be marked like this. Various points in the coil. This is A, this is B, this is C, and this is D. Of course, here there is an opening here. Okay. So here there is a opening like this, and these points are connected to slip rings. Here you are having slip rings. The slip rings actually look like this. and these slip rings are connected with carbon brushes. So here you are having carbon brushes. The carbon brushes are connected to external resistor. So here you are having one more carbon brush. So this is carbon brush number 1, B1, this is B2. Okay, so this is the direction of the current in the external circuit. Here you will be having a resistance, load resistance R suffix L. So this is slip ring L R1 and this is slip ring R2. And of course here you will be having current flow like this. And you will be having electromagnets or magnets here. This is the north pole of the magnet. This is the south pole of the magnet. This is the south pole of the magnet. So here what happens is, okay, this coil ABCD, so that is called the armature coil, and that armature coil actually rotates through this axis. Okay, that undergoes rotation about this axis with some angular velocity omega. Okay, this coil actually rotates about this axis, and for the different positions of the axis, the angle between the area vector of this coil and the magnetic field, it varies. Okay, because you know very well the magnetic flux phi equal to B dot A. Okay, B dot A means it is BA cos theta. BA cos theta. Here theta is the angular displacement of the coil. So that is BA cos, angular displacement is cos omega t. So this is magnetic flux. And you know very well the EMF is actually given by E equal to minus d phi by dt. That means you need to differentiate this equation with respect to time. So when you do that, what you will be getting? So before that, here the coil may be having n number of turns. So in that case, you will be having n as well. Okay. So when you have n and when you differentiate this, what you will get? You will be getting NBA into sine omega T. NBA omega. Of course, you will be having omega here. Sin omega T. So EMF. The EMF induced in this coil due to the rotation of the coil. When the coil rotates, what happens? This angle changes. Okay, this theta changes because this coil is placed in the external magnetic field due to the pole pieces, north and south. Okay, so the plane of the coil, that angle made by the plane of the coil with the magnetic field changes, and due to the rotation of the coil, an EMF is induced in the coil, and that EMF leads to the induction of current. Okay, that EMF leads to the induction of current in the coil as well. So in the external circuit, the direction of current flow changes from B1 to B2 and B2 to B1. Okay, in the external circuit, the direction of current changes periodically. That's why it is the alternating current, and of course the magnitude also changes, because here you see this NBA omega is the maximum value of the EMF. Okay, so here E equal to E naught sin omega t. The EMF varies according to this equation, where this E naught is nothing but NBA omega. That is the maximum value of EMF. So the EMF varies sinusoidally like this. E equal to E naught sin omega T, and E naught equal to NBA omega. NBA omega is the maximum value of the EMF. Okay. And now how will you calculate the induced current? That is, the induced current can be calculated by this equation. I equal to epsilon divided by RL. That is the load resistance, because the output is actually taken across the load resistance only. So I equal to E by RL. So that means E is nothing but E naught sin omega t divided by RL. I. Okay. So here this E naught by RL is nothing but I naught. That is the maximum value of current. So since the EMF varies sinusoidally, the induced current, it also varies sinusoidally. I equal to I naught sin omega t. Okay, I equal to I naught sin omega t. EMF varies sinusoidally, so current also varies sinusoidally. So this is the working of the AC generator. Okay. So for the different positions, okay, for the different positions of the coil, due to the rotation of the coil, you are getting alternating current that varies according to this equation. Okay, and this is all about the AC generator. Okay, actually, are you people actually attending the test regularly, students? Are you all attending the tests regularly? Students, please respond. Are you all attending the tests regularly? I have been forwarding the question papers.
Yes, sir.
Yes, what about the other students?
Attending, sir.
Okay. So, attending the tests is very important. Then only we will be getting the sufficient amount of practice, and you will be getting good command over the concepts, and you can solve the problems easily through practice only. So that's why you are getting the test papers. Okay. So tomorrow you will be getting a question paper consisting of 25 questions in electromagnetic induction. Okay, tomorrow evening you will be getting the question paper, so you should be prepared well, and you should be able to solve most of the problems, hopefully. Okay, so in that way only you can improve your scores in the NEET exam. Okay, through consistent practice, you can get good marks. So, anyone having any difficulty in electromagnetic induction, in the concepts or understanding the concepts of electromagnetic induction? Anyone have any difficulty? Can you understand the concepts easily?
Yes, sir.
Yes, I hope in your schools they would have completed this portion, right? Electromagnetic induction.
Not yet, sir.
Not yet.
Completed, sir.
Completed. Okay. So in that case, you should be able to understand the concepts easily. Okay, if these chapters are already completed in school, so please revise the concepts regularly and attend the test regularly. And I would like to remind you once again that tomorrow you will be getting a question paper consisting of 25 questions in electromagnetic induction. So attend the test. Thank you so much for joining the session. Let us keep it this much, and we shall meet again in our next class with a new lesson. Okay, and of course, in the next class we will be discussing the solutions for the question papers as well. Okay, that's the first thing we will be doing in our next class. The question paper which I will be giving you tomorrow, solutions for those questions will be discussed in our next class. Okay. Thank you so much for joining the session. Let's meet again in our next class. Thank you.
Thanks, sir.